Okay, classwork 2.5. You actually already know how to work with numbers 1 and 2. I don't know if you've necessarily worked with just some generic looking graph before. So what I'm wanting to do is just take you through a very slow step-by-step process. And we're going to always start with the table. So with the table, we know that if these are the x values, that creates these f of x values. So -4 gives me an f of x that is 5. -3 gives me 3. Basically, I can copy paste this f of x column all along here. Now, f of x plus 2 means add 2 to what you have. So 7, add 2, 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 add 2. And then I'm going to move this table out of the way. And I'm going to plot these points, but when I plot them, I need to ignore this middle column. I need to plot -4, 7. And then I need to plot -3, 5. So -4, 7 is this point right here. -3, 5. -2, 3. -1, 1. 0, 1. 1, 1. And then 2, 2. 3, 3, 4, 4. So realize that on the original table, these are just particular designated points. And I can't seem to plot them well at this moment. And this is showing you what has happened to those points when you're given a function and then you're told to add a number to that function. And then if you look at what that creates, that has shifted the graph up too. And you should expect that from what you've done in the past. For the next table, we're going to look backward. What I have here is we are starting with the column for the answer to F. And now listen really, really, really carefully. I want you to see that what I am highlighting in blue, those match. What I am now highlighting in blue, those match. I am going to highlight in green the fact that this is F. That means that this column must match this column. So what it's saying is, if you have x minus 2 values, and that's what's going into your function, and you already know that this is the relationship, these go in, boom, these come out, then this column must be this one. So we're going to write that column in: -4, -3, -2, -1, 0, 1, 2, 3, and 4. But then we want to look at, if this represents x minus 2, then what does x have to be in order for these to equal x minus 2? In other words, if x minus 2 is equal to negative 4, what is x equal to? And you get negative 2. And then negative 3, if x minus 2 is equal to negative 3, then what does x equal? Negative 1. What am I doing to go from this column to this column? Does everyone see that what I'm doing is I'm adding 2? So negative 2 plus 2, negative 1 plus 1 plus 2, 0 plus 2, 1 plus 2, 2 plus 2, 3 plus 2, 4 plus 2. Now I'm going to take this and I'm going to move it out of the way. And then I want to plot the xg coordinates. If I'm going to graph g, then I want to, for these x's, plot these y's. And the only way I personally am not going to mess up is if I block out this column. And then I plot the points. Negative 2, 5. Negative 2, 5. Negative 1, 3. 0, 1. 1, negative 1. 2, negative 1. 3, negative 1. 4, 0. 5, 1. And 6, 2. And take a good look at it, and you should see that you have the same graph. But it has been shifted right too. Now take a moment to also remember that if you took y equals x squared and you were told to make it to then graph y equals x minus 2 squared, you see the minus 2, but you actually go right to. I want you through this classwork to see why it moves right to instead of left. And just take some time to contemplate what happened here and maybe look over it again. And I'm going to move on to the next problem. I'm going to do this one a little bit quickly. If I'm going from x to f of x, then I'm basically just writing this column down. So I'm just going to write it down real quick. 5, 3, 1. Negative f of x just is multiplying by negative 1. If I multiply 0 by negative 1, it's still 0. And then if you plot those points, you will get what you expect to get, or at least hopefully what you were expecting. Ignore this middle column. And if you plot those points, you're going to see that you're getting an exact reflection over the y-axis, or sorry, I almost said the wrong thing, over the x-axis. Do you remember that that's what we do when we multiply by -1, we flip it upside down? But I want to show you that this is like a gymnast rotating around a high bar, where this is the high bar, the x-axis. So they're holding onto it with their hands. That is where it stays the same and everything else flips upside down. We're getting the point 4, -5. I'm sorry, -4, -5, which is this point reflected. We're getting -3, -3, which is this point reflected. -2, -1, which is this point reflected. -1, 1, which is now this point reflected. And let's see, 0, 1, 1, 1, 2, 0, staying the same. 3, -1, 4, -2. And when you connect the dots with the same shape that we were working with, you should see that it gives you that reflection over the x-axis. Now we did this, what I'm about to do, we did this already last Friday, and I want to do it again to make sure it's clear. And this is showing up on today's quiz as well. So I want to point out to you that the input of F right now is column 2. So whatever I'm getting for my f of x column, I look at who's the input, that column gets these. So my -x goes in, that's going to be all of these. So that's -4, -3, -2, -1, 0, 1, 2, 3, 4. If this column is -x, then to get this column, I have to multiply those x's by -1. And then when I plot those points, I see something different from what I got in number 3. So I can plot the point +4 for x, -4 for y. Oops, you know what I didn't do? I didn't cross out my middle column so that I would not look at it. I always have to cross out my middle column. Try again. 4, +4, +5. +3, +3. +2, +1. +1, -1. 0, -1. -1, -1. -2, 0. -3, 1. -4, 2. Do you see that each of these points was a reflection from the opposite side of the y-axis? When x is multiplied by -1, before it goes into the function, that horizontally flips it around over the y-axis. And don't forget that when the quiz comes around today. Now, what I've gone over so far, we have talked about to some extent, but I'm heading now into some other territory. I'm going to start off with something we have done, and then I'm going to move to something we have not yet done. And the reason, maybe this feels like it's going slow for you, but there's a reason. Now, I want to point out that we have our x and our f of x. So I'm just going to match these columns right up. This column will be 5, 3, 1, negative 1, negative 1, negative 1, 0, 1, 2. Now this column is telling me that I'm going to take those values that I just wrote down and I'm going to multiply them by 2. So I have 5 times 2, 3 times 2, 1 times 2, and times 2, times 2, times 2. 0 times 2, well, that's not going to do anything. 1 times 2, and 2 times 2. Then I'm going to eliminate the middle column so I don't accidentally write the wrong points. Just ignore it. All right. Now I'm going to plot these points the best I can. However, some of them are going off grid because this grid only goes up to 8. So I can't really plot negative 410 on this grid unless I decide to extend it. I'll go ahead and just show that a quick extension. So it's about here-ish. Negative 3, 6. Let's plot it. Negative 2, 2. Negative 1, negative 2. 0, negative 2. 1, negative 2. 2, 0. 3, 2. And 4, 4. And now I'm going to draw what that is doing. And I want you to notice that, provided I can draw it accurately, the points on the x-axis held on to the x-axis. Because if you multiply a y value of 0 by 2, it's still 0. All of the other y values were doubled. And that causes it to stretch vertically by a ratio of 2 from the center x-axis. But anyone on the x-axis stays on the x-axis and holds on for dear life, where everyone else is stretched from there. Now you have done that before, but this next one you may not have done before. So follow me carefully. If this input is the input for function f, then these values for function f come from input values here. And I'm going to put those numbers down. Stay with me here. Negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, and 4. I want to know what x is equal to in order to get 2x. So if 2x is equal to negative 4, then I divide by 2, and I get that x equals negative 2. If 2x is equal to negative 3, I divide by 2, and I get negative 3 halves, which is negative 1.5. I'll put negative 1.5. And then next I have 2x equals negative 2. Divide both sides by 2, and you get that x has to be negative 1. Negative 1 divided by 2, or negative 0.5 if you like. Now, what's 0 divided by 2? Still 0. 1 divided by 2 is a half. 2 divided by 2 is 1. 3 divided by 2 is 1.5. 4 divided by 2 is 2. So I want you to see that in order to go from what's in the function, 2x, back to original x, I have to divide by 2 to find what those numbers are that need to first be doubled and then create the function. Now let's plot these points to see what happens. Top one, oh, before I almost did it again. I'm going to eliminate the middle column so I don't accidentally put that down. And now I'm going to plot the points, -2, 5. -1.5 and 3. -1, +1. -1/2, -1. 0, -1. Then 1/2, -1. And then 1, 0. 1.5 and 1. 2 and 2. And now let's connect those dots and see that what happened was the graph got horizontally squished or compressed into the y-axis. The only number that did not change was when x was 0. That could not have been changed, because 0 times 2 is still 0. Everybody else, the x-coordinate had to be divided by 2 before the function took place. And then the same y values came out. Now, what I want you to observe from all of this, the operation that you see on x, you see multiplication. The opposite of multiplying is dividing. So if you see multiplication to the x, you're going to divide the x's by that number, and then that tells you how it squishes. And then we can continue doing the same thing, but let me show you what I have on the answers to help you a little bit. I've done some color coding to help you. So I'm going to move to the one we just did. We just did this one. And I want you to see the color coding. I've got green, kind of a yellow, orangish yellow, and a blue. These points, this is what happened with their x's. You started at -4, you divided by 2. For these two, here are the points. They kept the y value of 2, but the x-coordinate of 4 was divided by 2. And then for these 2 points, it was dividing by 2 to get -1/2 for the x. So is that making sense of what's happening horizontally? And I want you to see that I also pointed out vertically for the previous problem. You can see that this original y value was doubled and then showing you on the y-axis. This y value got doubled, and you can see that on the y-axis, and the same with blue. These were the points. This shows you on the y-axis that it was the vertical that was changed. When you are asked to change the graph by multiplying outside the function by 2, you multiply the y-coordinates by 2 and keep the x coordinates as they are. When you have multiplication to the x inside the function, you keep the y values as they are, and you take the x values that you began with, and instead of multiplying by 2, you divide by 2. You always do the opposite operation horizontally because you're actually having to go backward. Whereas when the operation happens outside the function, you're heading forward. So you do the operation to the y values. But to go backward, you do the opposite operation. So with all of that, what I'm hoping for you to conclude is the following. The multiplication or division outside the function stretches or compresses vertically, and it does multiplication. But if you see multiplication inside, that stretches or compresses horizontally, but you are going to take the parent graphs x coordinates, and that's coordinates, and you are going to divide them by b. Keep the y values as they are, but divide the x coordinates by b. When you have the multiplication outside the function, you take the parent graphs y coordinates and you multiply them by b. Or sorry, by a. And that will allow you to find exactly where that stretched or compressed to. And I want to point out to you also, if the number you multiply outside the function is greater than 1, that's going to stretch it vertically. But when it's x being multiplied, if it's being multiplied by a number that's greater than 1, that's going to compress it horizontally. And then the difference between multiplying outside the function by negative x causes the y coordinates to reflect. Multiplication inside the x causes the x coordinates to reflect as it spins around. If you see addition or subtraction outside the function, then it's a translation in the same direction. But when the addition subtraction is with the x, it translates it horizontally in the opposite direction. I'm hoping you can come to a really big conclusion here. And that is, you can really combine all of this into, if it's an operation outside the function, do that operation to the y coordinates, keep x the same. But then in the right column, if the operation is happening inside the function, do the opposite of that operation to the x's and keep the y's the same. I want to point out that when you do multiply if you want, you can look at the multiplication by -1. The opposite operation would be divide by -1, which is actually going to do the same thing, but it's to the x. Whereas this multiplication outside is to the y. So the operation outside the function affects y. The operation inside the function affects x. That outside operation affects y by doing that operation to your y's. And then over here, that operation to the x does the opposite operation to each of your x's. And if you can see that general principle, that's going to save you so much, because that means that the rest of this class, the only thing that will be new is learning new parent graphs. But how we stretch and move them and reflect them, that's universal. Now, I've got a quiz I need to open up for you, and we've got 6 minutes left in class. So if you finish the quiz early, you can leave early. And I'm going to get that quiz opened. Just need to get over to it. Okay, assign. Oh,